So, what we have done in earlier classes, we understood basics of design of the battery pack, fundamentals of battery pack design. In that, first we understood that what are the discipline we should follow to do a proper design of a battery pack. What we found that if we go through properly in the 4 aspects or 4 discipline, and what are those? Electrical design, then mechanical design, then thermal design, and then BMS and embedded system. So, what we have done till now, we have gone through the electrical design. In the electrical design, various aspects, current, voltage, capacity, then current path, voltage drop. Then we have come down to mechanical part. In that we understood various aspects of loading of the battery pack, how should we design the base plates, side plates, tie rods, and external casing. Then we have also gone through what would be impact of vibration, and then we have concluded that particular section. Today we will start thermal design of a battery pack. Bits and pieces we have been discussing thermal aspect from the electrical design of battery pack itself. Here we will go slightly in depth. The many unanswered question what we didn't do, what we didn't explain it properly at that place, we will try to explain it here. We will also try to understand what would be the proper way to select a thermal management system. Before selecting, to find out the requirements, what is required for a thermal management system, and then a design of thermal management system. We will also look upon some of the studies what we have done here, which would help you to take a comparative study or a benchmarking study for your work whenever you wanted to do. So, let us move ahead. Thermal design of the battery pack, that is section 3, and then we will have a BMS and embedded system in the next class. So, when we say thermal design of the battery pack, what happens? So, let us take 2 examples here. We have a pack A and we wanted to see the behavior of that pack A. The pack A is working at 50 degree centigrade and it gives me 800 cycles, and then pack capacity comes down to 40%. After 800 cycles, the pack capacity comes down to 40%, or you in other way, when I am saying 40%, that means the overall capacity also I can say has reduced by 40%. As soon as you increase the working temperature of the pack, that means now pack is being utilized at 55 degree centigrade. The number of cycle has come down to 500 cycles. Also my pack capacity has come down to 30%. Here in the first case my pack capacity has come down to 40%. Initially we had 100%, then it has come down to 40%. Initially we have 100% capacity at 50 degrees centigrade. After 800 cycles, the pack capacity has come down to 40%. That means now pack can take only 40% of the energy, and also it can give you only 40% of the energy. Now the same pack, when my ambient temperature is 55 degrees C, So, there are two things happens. Not only the cycle life has come down, now cycle life has come down to 500 cycles. At the same time, my pack capacity has gone down to 30%. So, there is a, if I have to compare apple to apple, so this cycle may be further down, maybe 300 cycles, maybe 250 cycles. If the pack capacity is at 40%, in that case my cycle life may be 250 cycles. So, what do we see? A change in 5 degree centigrade in ambient condition itself has brought down the number of cycle as well as capacity. Now, look upon other pack, a pack B. At 45 degree centigrade, it takes 3323 cycles for a capacity degradation of 90%. That means I have only 10% capacity left. At 45 ambient, a pack B, other pack, goes to 10% of the capacity, that means 90% capacity degradation. The total number of cycle is 3323. Now, the same pack when operated at 60 degree ambient gives me only 1037 cycles, more than 3 times or less than 3 times cycles by just change in 15 degree of ambient temperature, and the capacity is 10%. So, here I am doing apple to apple comparison, I am only showing you the effect of temperature here. In the first case, for 800 cycles 40% capacity, for 500 cycles 30% capacity, however, the temperature is 50 to 55 degrees centigrade. In the second case, 45 degree centigrade at 45 degree ambient condition, my cycle life is 3323. The pack capacity, the remaining pack capacity is only 10%. At the same pack at 60 degree centigrade is giving me 1037 cycles only. So, a change in 15 degree cycle, 15 degree ambient condition has brought down the number of cycles by 1/3 or less than 1/3, keeping the same capacity. However, in EV application, as soon as my pack capacities goes below 70% or 75% or 80%, depend upon OEM to OEM, we say now this pack is no more usable for EV application. It does not mean that it has gone completely bad. For EV application, it is no more usable. However, we can use it for some other thing, like for energy storage, like for UPS system, second life of the battery, for stationary application, or in the low end EV application itself. Like if we are using it for cars, we may be able to use it for two-wheeler, low speed two-wheelers. So, what happens? Temperature of the pack directly impacts, what are the things it impacts? Electrochemical reaction. At higher temperature, these electrochemical reactions are generally fast, and since these electrochemical reactions are fast, there is always a capacity fade because of that, because the reactions rates are very fast. It is not optimal, it is fast. At lower temperature, the electrochemistry becomes very slow, various reasons. The electrolyte viscosity increases, internal resistance increases, and because of that, it does not give you the sufficient power and energy, mostly power back to you. Same thing happens while charging also. So, the temperature of the pack directly impacts the electrochemical reactions. Then what else? Efficiency of the pack. When I say efficiency of the pack, the losses becomes more at extreme temperatures, either in the lower side or on the higher side. Lower side, because of the increased internal resistance, you have the thermal or you have a heat generation more, and it's basically wastage of the energy. At the higher temperature, and we also say that as a sluggish chemistry, sluggish electrochemistry. At the higher temperature, reaction rates are much more than expected. So there is a more capacity fade. And because of that, again your pack efficiencies come down. Charge acceptance. At higher temperature, if you charge at higher rate, what will happen? Since already temperature is high, now more heat is getting generated. So temperature rise would be very fast, and that we will not be able to control. And because of that, it is possible to have a thermal accident. At lower temperature, again internal resistance is very high. So you try to charge it or discharge it at higher current, there would be more heat generation. Because of the more heat generation, there would be localized heating, and because of localized heating, there might be possible that the separators, which is generally made of polymers or electrolyte, get decomposed, separator get melted out, and because of that, again there might be a thermal accident. Power and energy availability, same concept. At higher temperature, you still have power available, but you cannot take out because it will give you the steep rise in temperature. At lower temperature or negative temperature or towards zero temperature, again the same phenomenon will happen. So you cannot say that power and energy availability is 100% at higher temperature as well as lower temperature. Safety and reliability, both side, on extreme side, on higher side, and that as well as lower side. Things are beyond your control. You cannot control the things. At higher temperature, if heat further penetrates or further heat gets generated, that would make the cells unstable. At the lower temperature, there could be a local heating if you are trying to take the more current, and that is what is power and energy availability. And it has a higher internal resistance by virtue of its components or its constituents. What happens? Again, you cannot take out a lot of energy. So you have to ensure the minimum current during the lower temperature as well as the higher temperature. As soon as you are ensuring that, what will happen? Whatever is expected power, you will not be able to pick up, and there will be wastage of power, wastage of energy because of the heat generation or higher reaction rate, electrochemical reaction rate. In both the cases, you have the energy loss. So energy availability is also not sure. Safety and reliability, the same thing. At higher temperature, there is a possibility that your temperature rise very fast, which you will not be able to control. At the lower temperature, temperature rise will not be very fast, but might be local heating, local hot spot. Life and life cycle cost. This is what exactly we explained using these two graphs. So if you are maintaining a temperature at 45 degree, you would be able to get much more cycle than at 60 degree. So there is always a optimal temperature band, which we will talk later. What is the required function of a thermal design? What should we do, or so that such type of things does not happen? So if you see in the picture here, it's a cylindrical cells, and it is not managed properly thermally, it is not thermally managed properly. So what happens? It has gone to the thermal runaway case. What happens? Initially the gas, because of the electrochemical reaction, because of the higher temperature, a gas vents out, and seconds after that it's burned completely. Similar is a prismatic cells here. It has gone in thermal runaway. You can see here this whole cell has burnt out completely. So what would be a required function of a thermal design? Certainly we don't want to have this type of situation ever. And when we don't want to have this type of situation, we need to prevent that by having a proper thermal design. And what are other attributes of a thermal design? The first one is compact, because in a vehicle the space is at premium. You wanted to pack more and more energy, not supplementary function. Thermal management system is a supplementary function at the vehicle level. It is important for the battery, but it does not give you energy. In fact, it takes energy. So you wanted to have as small as possible, as compact as possible. It adds weight, and that weight is not a cell weight. It is on and over the cell weight. And when it is on and over cell weight, what happens? Your energy density will come down, both gravimetric as well as volumetric. When your energy density will come down, then what will happen? You will take more space, you will increase the weight, and as soon as you are increasing the weight, what happens? Your range is coming down. In chapter 3 or chapter 2, you have done the vehicle dynamics. What happens? Your range is direct function of the weight of the vehicle. Correct? So it has to be as lightweight as possible. At the same time, even though space is in premium, we have to design in such a way that we can still package thermal management system properly. And most of the places, it's not only it cools the battery or it manages the battery, it also manages the cabin. So it should be easily packageable within the volume of the vehicle. Reliable. If it does not function properly through its whole life, what will happen? We can have the situation like this. If my cell is robust, if my battery pack is robust, and the thermal management system is not robust, one by one everything else will start failing. So the thermal management system has to be reliable. And when I say reliable, it is not only its performance, reliability, it should also work well during the on the Indian road, during the various ambient conditions, because ambient is not fixed. In Chennai, we have temperature something between 25 to 45. In Delhi, we have a temperature between something 2 degree to 50 degree. In Rajasthan, most of the time we have a temperature 45 plus, goes up to 55. In Leh and Ladakh, most of the time temperature would be minus 20 to 15 degree. So and you cannot design the multiple thermal system which can cater at those places. You will have a unique design which will work from this end to that end, from negative end to positive end, minus 20 degree to 55 degree, or in some cases, some extreme cases, even minus 40 to 55 degree or 60 degree. it should be easily serviceable. Even a highly reliable pack may go with some problem, and whenever that problem comes, we should be able to service it easily, because if your service is not easy, what will happen? It's added cost, it's added man cost, it's added material cost, and you already have a huge upfront cost because of the cell. Rest of the places you wanted to reduce as much as possible. So in design itself, we need to look upon the pack is easily serviceable. Low cost. There are thermal management systems available which can work anywhere, anything, but then the cost is so high I cannot adopt. So my design should take care with the extreme range, I should still have the minimum cost. Low parasitic power. From where thermal management system draws its power? It's from the battery, and the energy is at premium. If I don't manage the energy consumption by thermal management system properly, what will happen? I have to increase the energy of the pack, and as soon as we are increasing the energy of the pack, what happens? You are increasing the cost, you are increasing the weight. That might not be packageable within the given volume of the vehicle, packaging space in a vehicle. So the losses in the thermal management system should be the minimum. In other words, the efficiency of the thermal management system should be maximum. Optimum temperature range. When I wanted to run in the Leh and Ladakh, I will try to run on the lower range side. When I wanted to run on Rajasthan, Jaisalmer or Delhi in the summer, I wanted to run on a higher temperature band. So that my losses because of the ambient condition, my energy losses because of the ambient condition should be minimum. Within the pack, there should not be much differential temperature gradient, because even if I am managing out of 100 cells, I am managing 99 cells at the optimum range, and one cell is deviating a lot, the pack capacity, the pack availability, the pack power depends upon that one cell, which has the minimum capacity. So if I maintain the temperature variation within the limit, and that generally acceptable limit is 2 to 3 degree, in extreme cases 5 degree, my differential degradation will reduce. So that means all the cells will work at the similar level throughout the life of the battery pack. What is the battery pack temperature consideration? We were just talking extreme condition at higher side and lower side. Battery cells works well, or I can say great, between 15 degrees C to 35 degrees centigrade. Here we have optimal impedance, we have an optimal reaction rate, the power and energy availability is optimal in this temperature range. Life cycle is also optimal in this temperature, 15 to 35 degrees centigrade. So I always want to run the thermal management system or a pack which can maintain the temperature between 15 to 35 degrees C. If not, at least close to that. Why I say if not? Because there are passive thermal management system which does not draw the battery pack, but you don't have too much control over that one. So at high temperature, the primary considerations are life, safety, such that thermal runaway or any thermal accident should not happen, and non-uniform aging effect. If the temperature differential between the cells within the packs are too much beyond your limit of whatever you have said 2 to 5 degree, then there would be a differential aging, and that weakest cell ensures what is the pack power and pack energy availability. So, you do not want a particular cell to become weakest. So, all the cells should be in the similar health level. In that case, cooling is required in hot environments, moderate to large current demand. Whenever you are taking moderate to large current, what happens? Heat generation is high. Joule's heating we have studied during the electrical design, I square R is very high. So, in such cases again we require cooling of the battery pack, even though ambient condition is 25 degree or 30 degree. Fast charging, when I say fast charging, you are putting back a lot of your current, charging current is very high, that is why it is a fast charging. Even in that case again the same rule applies, I square R, your heat generation is very high. So, you need to remove that heat. At low temperature what happens? The primary considerations are, first one is performance, that means power is available, energy is available. Damage due to the fast charging should not happen. What should we do? In such cases, heating of the battery pack is required in the cold environment during the charge as well as discharge. The next is heat generation in a battery pack. So, what we understood, the temperature optimum temperature is 15 to 35 degrees C. Then we also understood when cooling is required, when heating is required, but how much cooling, how much heating. So, for that we need to understand what is the heat generation in the battery pack. So, we will discuss primarily Joule heating here today. So, heat generation in a battery pack at macroscopic view can be modeled as a Joule heating, and that is nothing but heat generation is I square R, current square into internal resistance. Where it can happen? It can happen in cells, it can happen in bus bar, it can happen in BMS. Now, this allows us to estimate heat generation for battery pack thermal management. It allows you to find out the problem. Once you know the problem, then only you can solve it. So, it gives you the problem statement. To design a thermal management system, you need to know the heat load, and that is what is here, heat generation. A part of heat load is heat generation. Now, the problem is that this internal resistance, what we say here, that internal resistance is dependent upon several other things. In the cells, it depends upon the temperature of the cells, depth of the discharge of the cell, and open circuit voltage. There might be some other parameters, but that is not so significant, but these three parameters are very significant. In the bus bar, temperature, in the BMS again temperature. So, when I say heat generation in last slide, so now I am saying that as a heat load. Let us assume there is no environmental impact on the battery pack because of the temperature difference and other thing. So, in that case, what would be the heat load of the battery pack? So, what we have done earlier is 2P16S pack in the electrical design as well as the mechanical design of the battery pack. Use the same pack, same cells, one new terminology got added here, internal impedance or internal resistance as 10 milliohm, and the module is discharged from 100% to 20% SOC at the rate of 1C. When I say 1C and the 2P is the configuration, what would be the current? 28 ampere, but for one cell it would be 14 ampere only. If two cells are parallel, then it is 28 ampere. If I am considering one cell, then it is 14 ampere only. Now what it is saying, calculate the heat generated and energy expelled by the module and compare energy lost as a heat to the total module energy in discharge duration. Now what we have? We have, it is a mistake here, it is a 14 ampere here. Current at the rate of 1 C is a 14 ampere here in every cell. So now cell internal resistance is 10 milliohm. So what is the heat generation in per cell? 14 into 14 into 10. How much it comes? 1.96 watt. Now how many cells we have total? Total we have 32 numbers of cells. So total heat generation of the pack is 62.72 watt. So energy lost by the pack as a heat, that is what we have to find out. For 100% to 20% SOC, the time taken is 2880 seconds. Now heat energy lost is 5.64 kilojoule. You multiply 62.72 watt by 2880 seconds and that would come on 5.64 kilojoule. Heat lost by the pack is 180, sorry, this is at 1 C, what we have said is 1 C. This is for each cell, 5.64 kilojoule is for one cell. Now heat lost by the pack, total pack, that means 32 cells together, multiply this with 32 cells. So that becomes 180.63 kilojoule. So now what is the total pack energy? Total pack energy from 100% to 20% SOC, we have 4000, consider a linear relationship here. So that is a 4709 kilojoule approximately, and in that we have a heat loss of 180.63 kilojoule and that comes to 4.1%. So approximately 5%. So 5% energy is lost only because of the heat generated. Now it is not only the 5%, now you need energy from the pack to remove it. So it could land up somewhere 6%, 7%. So 6 to 7% of the energy of the pack which could have been used for extending the range is lost because of the cell and subsequent thermal management of the pack. So what we see, around 4.1% of the pack capacity is rejected as a waste heat. It is not useful, you cannot use it for anything. When your SOC is 100, when you bring down the SOC from 100% to 20% at 1 C rate, what are the things we have to do? When I say 1 C rate, it was 14 ampere. If I reduce the C rate, let us suppose 0.5 C, what would be the current? 7 ampere. And if the 7 ampere current is there, then my heat energy lost would be 1 by 4 times. That means this 4.1% will come down somewhere 1%. Another way, if I select a cell where internal resistance is very low, let us suppose 1 milliohm, again my heat generated in the pack would be much lower. So the combination of this both together, we try to reduce the wastage of the energy in the form of waste heat. Any question till now? So how do we transfer the heat? So let us understand energy flow through first principle. Whenever heat get transferred, it always happens between when there is a temperature difference or where there is a temperature differential, and it always happens between higher temperature to lower temperature. So, this is hot object and this is a cool object, and heat always flow between hot object to the cooler body, and that happens because of the temperature differential. There are different modes of heat transfer: conduction, convection, and then radiation. The heat transfer Q is Ka delta T, where K is the thermal conductivity, A is the surface area, L is the length, and T2 minus T1 is delta T, temperature differential. In the convection, Q is HA delta T, and in the radiation is Q sigma A epsilon T to the power 4 minus T1 to the power 4. And these all things can be converted into thermal circuit analogy as electrical circuit analogy, where heat flow Q is delta T by RT conduction T1 T2, current flow I is B1 minus B2 by RE, where B1 B2 RE.